In the last lecture, we looked at the optically thin and thick limits. So, these limits provide a good insight as regards what happens during radiation when the photon mean free path is very small or very large. If you recall, the total optical depth, which is this quantity, if this is much less than 1, that is, the photon mean free path is very large compared to the spatial scale of the system, then we saw that the divergence of the radiative flux was equal to radiation absorbed from surface 1, from surface 2, and what is emitted by the surface. So, in the thin limit, you find that the interaction is between the gas and the two walls, that is absorption term, and what the gas emits in both above and below the interface. Now, this is the thin limit. In the thick limit, we had derived and we got a result for flux as a simple differential equation. Now, these two look very different. Let me just also write the radiative flux for the thin limit for comparison here. In the thin limit, if you recall, the QR lambda is very simple, nothing but difference in radiosities between the two. So, in the thin limit, the flux through the medium did not depend on the gas, it merely depended on the radiosity of the two sides, while in thick limit, you have a differential equation. Here you have an algebraic equation. So, the basic nature of the radiative flux expression has changed dramatically. In one case, the flux depends on the local gradient of the emissive power of the gas radiation, while in the thin limit gas plays no role. The radiative flux is merely the difference in the radiosities of the two walls. So, it is important to understand this important difference in the two limits. In the thin limit, the gas plays no role. Gas does not play any role at all. It allows the photons from one wall to go to the other wall and vice versa. The photons from the other wall go back to this wall. The medium is completely passive, it does not do anything. On the other hand, this is because the photon mean free path is so large that the photon is essentially untouched as it goes from one wall to another wall. Okay. So, the gas plays almost no role in the flux. But if you look at the thick limit, the radiative flux does not depend on what is happening in the wall. Wall play no role in here. Everything depends upon the local gradient of the black body emissive power of the gas emission. Okay. So, the thick limit, at any point inside the gas, the radiative flux depends upon only the local gradient of the black body emissive power at the gas temperature, and has nothing to do with the two balls. This is because the photon mean free path in this case is so small that photons which are emitted little far away from the interface you are interested in will not reach your location. The photons emitted by the ball will not reach the gas. So, at any location the gas only sees the adjacent layers from where the photons come. If the layers are a little far away, the photon cannot reach this layer. So, this is completely local control. Now, I want you to appreciate the fact that this kind of phenomena where everything depends on local gradient is happening because the photon mean free path is very small compared to the length scale of interest. Which in this case is L, which in this case is 1 over A lambda. So, 1 over A lambda is very small compared to the length scale of interest, that is the distance between the plates. Then everything is controlled locally, and we saw q r lambda is equal to minus 4/3 d E lambda b by dx. Now, I want you to realize the same logic is applied to conduction heat transfer. In conduction heat transfer, the molecular mean free path, not photon, molecular mean free path, that is the distance traveled by a molecule in a gas. This is a gas conduction. Let me remind you, this is gas conduction. Conduction gases is small compared to the length scale of interest. Then all of you know that Q conduction is minus K delta T So, I want you to see the parallel between these two basic situations. So, in radiation, when the photon mean free path is small compared to the length scale of interest to us, then everything is locally controlled, and hence the radiative flux depends only on the local gradient of the black body emissive power. For the same reason, in gas conduction heat transfer, when the molecular mean free path is small compared to the length scale of interest to us, then the conduction heat transfer is proportional to temperature gradient. Now, these two expression for fluxes are not really same. This one is watts per meter square per micron, this is watts per meter square. So, you may be having some difficulty comparing these two. So, next what we will do is, we will integrate this thing over all wavelengths to get the total flux. So, that comparison is more easy. So, Q r is nothing but 0 to infinity of spectral flux into d lambda. So, this will be 4 by 3 0 to infinity 1 over a lambda d E lambda b by dx, there is a minus I had to preserve here, d lambda. Okay. So, to do this integration in easy way, we divide and multiply by E b. Remember, E b is nothing but sigma d to the power of 4. Let us multiply that. So, that we will write Q r. This for convenience, this is not absolutely essential, but it makes our task a little easy if you do that. So, you multiply up and down by EB, you get dEB dx, you get dE lambda b by dEb. So, merely multiply and divided by this quantity d lambda. Now, since this quantity is independent of wavelength, I can take it out and I am left with quantities which depend on wavelength, which I need to integrate maybe numerically. So, this quantity is a number to be calculated once you know the variation of the absorption coefficient A lambda with wavelength, and this is a complex function, and we will spend quite some time in later part of the course explaining how this task is achieved. But right now, let us say you can do it, and this is called the Rosenland mean absorption coefficient. This integration is to obtain what is known as Rosenland mean absorption coefficient, and this by definition is 0 to infinity 1 over A lambda dE lambda b by dEb d lambda. Okay. So, this quantity can be calculated once it give me the temperature of the gas and the spectral properties of that gas. Today's tools we have with computers, we can calculate this and keep it for future use. So, this is the number which is function of temperature, which can be calculated a priori. So, that is available to you. So, with this definition, we can write down, and so Q r, which is what we want, is minus 4 by 3 dV by dx into 1 over A r by definition. Now, EB all of you know is sigma t to the power of 4. So, you can write it in a more simplified form as minus 16 by 3, this becomes sigma t cube, 4 sigma t, 4 has been absorbed here, 1 over A r delta t delta x. Now, we need to compare this with the Fourier conduction law. So, conduction heat transfer we saw was minus k delta t delta x. So, we compare this equation with this equation, you can define a new quantity in the thick limit. It is this quantity, this is k r, which is not a constant, depends on x. This is called radiation conductivity. And these are units of watts per meter degree Kelvin. The conduction that you know already from heat transfer background is also watts per meter degree Kelvin. So, it is possible for you to estimate the radiative conductivity of a gas given the Rosenland mean absorption coefficient. Now, most of you should be aware that for a typical gas, the conduction heat transfer conductivity is pretty low. You take air, it will be around 0.025 watts per meter squared, watts per meter degree Kelvin. So, let us see what kind of numbers we can get for the radiative conductivity. So, if I define radiative conductivity as 16 by 3 sigma t cubed by A r. Now, let us take a typical example. Let us say gas is at furnace situation at 1000 degrees Kelvin. Let us say we know that from our black body formula, this is, we know that it is a constant, universal constant. We just have to estimate AR. Let me take just for as an example, let AR be 10 meter minus 1. So, the photon mean free path is about 0.1 meter. Okay. So, in this case, let us calculate KR. KR will come out around 16 by 3 into 5.67 into 10 to the power minus 8, and this will be into 10 to the power of 9 by 10. So, all this will cancel out. So, this will be approximately around 30 watt per meter Kelvin. Now, you must recognize that in a gas, this is fairly high heat transfer rate, because typical gas conductivity, not radiative, but molecular conduction, is of the order of 0.03. So, what it shows is that if there is a gas at high temperature like 1000 degrees Kelvin, and the Rosseland mean absorption coefficient is of the order of 10 meter minus 1, then the heat transfer by radiation is about 1000 times more effective than molecular conduction. So, clearly at high temperature, we need to worry about the radiated heat transfer in this limit. Now, suppose instead of 1000 degrees Kelvin, we assume 300 degrees Kelvin, that is 1/3 approximately. So, 1/3 cube will be around 27. So, this will come to around 1 watt per meter degree Kelvin. Still, it will be much larger than gas conductivity. So, what must be remembered is that if you are in the thick limit, then the heat transfer by radiation is most often much stronger than heat transfer by molecular conduction, and must be accounted for in any given situation. And of course, you have to be sure that you are in the optically thick limit for you to apply this equation, which is a, so this limit is also called the diffusion approximation, because in the thick limit, radiation heat transfer behaves like a diffusion process. So, photon is being absorbed at a very short distance, and it is similar to what is happening in molecular conduction, where the molecules undergo collisions very often. So, the diffusion model is valid. So, there are examples we will see in later lectures, where this diffusion model can be used, and you can imagine that, especially in situations where we are looking at combined conduction radiation problems. It is convenient if you can treat both radiation and conduction as a diffusion process. So, imagine heat transfer in glass. You have hot glass in glass processing, then you have both conduction and radiation. And let us assume that the photon mean free path is quite short, so they can apply the thick limit. Then the total conductivity will be just the sum of molecular conductivity plus radiative conductivity. So, this is a function of temperature very much, and so in the manufacture of glass, you need to know, suppose there is a glass being molded or processed. In order to ensure that during the process of molding glass sheets, for example, for making all of you use television. The television, the front screen is made of glass, and you want that glass to be molded such that it is completely defect free. Then you have to ensure that there are no stresses in the glass during the process of freezing. And the molten glass is frozen to give the given shape of the TV glass, it has to be stress free. To be stress free, you have to keep the glass close to isothermal, that is, heat transient glass should be close to isothermal. So, you have to predict the temperature profile across this thickness, and there you have to account both for molecular conduction and radiative conductivity. And in these cases, as you will have guessed, this will dominate the heat transfer, the radiative conductivity. And so, this model, the diffusion model, using the Rosalind approximation, is quite common. So, you can see that this model of radiation heat transfer, where radiation is treated like conduction heat transfer, is quite useful, provided you can make the approximation that the photon mean field path is very small compared to the length scale of interest. So, we have looked at the two limits of radiation transfer, and we are able to do this analysis at the spectral level and obtain the two limits. But in solving the full problem, when let us assume that you are not able to make the approximation of the thick or thin limit. Now, this is quite common in radiation transfer problems. Now, why is that? Because if you look at the absorption coefficient of any gas as a function of wavelength, it has very complex behavior. This has been already mentioned, then I would like to repeat that issue. So, where A lambda is low, you may be in the thin limit. Where A lambda is large, you may be in the thick limit. So, you cannot assume at all wavelengths the gas is in the thick or thin limit, because there are regions where the gas will be in thick limit, there are regions with thin limit, in between it will not be in either thick or thin limit. So, the limiting case we just now saw is useful only to get some physical insight into the process of radiation heat transfer, but really not very useful in practice, except maybe in the case of glass, where the thick limit is reasonably valid. But in the case of gases, where the absorption coefficient as a function of lambda has such a complex structure, you cannot use the thick or the thin limit. So, we have to deal with the full problem. So, our next task is to ask how to solve the problem in the general case, when neither the thick nor thin limit is valid. What do we do? Now, before we go on to that, I want you to just understand how the basic problem we have looked at so far is modified when we have scattering. We will deal with scattering in little more detail in the later lectures, but right now it is good for you to know what is the difference in the basic equations. So, suppose you have both absorption and scattering. How will the basic equation of transfer change? So, let me write down this equation for a plane parallel model. You have both absorption and you have scattering coefficient. So, first part is the extinction, that is the decrease in the intensity on account of both absorption and scattering. Remember, in this case what is happening is along a path on account of either absorption, that is the absorbed photon, or photon scattering, you lose the photon in that direction. Either photon is absorbed or is scattered into some other direction. So, that is the first term. The second term is gain in photon, that is happening because of emission. And finally, one more term is coming which is not that, which is photon which are scattered from other directions. So, the way you look at it, here is the direction of your interest. So, photons coming in some other direction get scattered into this direction. You have to account for that, and this accounts for it. So, it takes the intensity in all other directions, and we assume azimuthal symmetry for convenience. If you assume we get 2 pi, and then with respect to this angle theta, you have to integrate the intensity in all directions . So, the basic equation transfer, which in the absence of scattering is the simple model we saw earlier, now gets a little more complicated in 2 terms. In the extinction term, there is one more term added because the photon is lost due to scattering. Then the photon is gained due to scattering in of photons traveling in some other direction into this direction. So, you look at photons in all other direction and ask what fraction is scattered into this direction, and that is calculated using this method. Now, all of you should be able to see that this complicates a problem enormously, because when this term was not there, the directional spectral intensity was only related to itself and the directional spectral intensity of a black body at the gas temperature. When you introduce scattering, this last term here links the intensity in all other direction to this direction. That means, you have to solve the problem of intensity in all directions simultaneously, because intensity in some other direction theta prime is linked to I prime lambda. So, this is what makes scattering such a complex problem, and so we will not be able to spend a lot of time in this course to look at this problem, but we will touch upon it briefly, so that you have some idea about how problems with scattering are tackled. But at this point, I want you to have an appreciation that if we introduce scattering into radiation transfer problem, the problem becomes one magnitude more complicated, because you cannot solve for the intensity in one direction in terms of just these 3 terms, but you introduce a term which connects the intensity in one direction to intensity in all other directions. So, that problem is inherently much more complicated than what we have posed here. We will get back to this problem later, but let us now look at much simpler cases. We looked at a thin and thick limit, and we pointed out that it is not always possible to look at these limits for gases, where the absorption coefficient is a strong function of wavelength. So, we will look at a very simple case. This is called grey gas. gray gas by definition is one where the absorption coefficient is not a function of wavelength. Now, this rarely occurs in the real world. Most gases have a strong dependence of the absorption coefficient on the wavelength, but we are going to use the gray gas merely as a teaching tool to tell you how the general equation for radiant heat transfer is solved. So, this is more a way to explain to you the techniques of solution. If the real problem involves a non-gray gas, then the entire thing has to be solved on the computer, and we have nothing to really show in the classroom very easily how the problem is actually solved. But an appreciation of how the equation is solved in your computer program is useful for the purpose of understanding the solution provided by a computer. So, we will go through the gray gas model, although we are fully aware that gray gas is an approximation which is not normally applicable in real situation. The only time gray gas model may work is when the gas is ionized. When the gas is ionized, then it can absorb a photon and take the gas from the bound state, and it comes out, and gas gets ionized, and the electron which was originally bound, it reaches a free state. Such an electron can absorb any frequency, because the kinetic energy of the electron can have any value between 0 and infinity. So, when the photons are energetic enough to knock an electron out of the gas and it moves freely, then such a gas can absorb radiation at all frequencies above a certain frequency, this delta E, and it will have a continuous absorption spectrum. So, as you can realize, in the case of astrophysics, where they deal with stars which are at very high temperatures, most of the gases are ionized. So, in astrophysics, the gray gas approximation is very useful. But in furnaces or in atmospheric science, atmospheric radiation, gray gas is not a very good approximation. But still, we are going to spend some time showing how equations are solved for gray gas, merely as a way to teach you how these problems are tackled. When the gray gas approximation is not valid, we need to extend the methodology to allow for the complex function of A lambda with lambda, but that is merely more computation, and that can easily be done today on the computer. So, our aim is that you understand the basic method of solution using gray gas as a useful example, but it is not a practical example. Okay. So, in the case of gray gas, the subscript lambda goes away, by everything is remember lambda. So, you can write down the basic radiative transfer equation as follows. The first term is the radiosity and the attenuation through the gas, integrated over all angles. Angle is built into this exponential integral function. Then you have a second term, which is the distance between the top plate and the given level. Then you have the emission from the gas below the level of interest to you. And finally, the gas above the layer of interest to you. So, of course, you need d kappa. So, this is an equation with all the lambda subscript removed, is the basic equation for radiative flux. Now, before you solve this equation, you can see if you want to solve this equation, you have to solve for some value of B 1 and B 2, and it will be nice if we can remove this B 1 B 2 from this equation by a suitable scaling. So, what we will do is, we will define a Q star, a non-dimensional Q, as QR by B 1 minus B 2. Note that in the absence of a gas, QR equals B 1 minus B 2, this is equal to 1. So, this is a good thing to remember, that Q star is so defined that in the absence of a gas, this is equal to 1. We define a non-dimensional temperature as sigma of the gas, sigma of the gas minus radius of S2 by. So, these are convenient definitions. It is done such that the final equation, the non-dimensional one now, is nothing but Q star equals 2 E 3 kappa plus 0 to kappa phi of kappa star E 2 of kappa minus kappa star d kappa star minus 2 kappa to kappa 0 phi of kappa star E 2 of kappa star minus kappa d kappa star. So, notice that this equation is much cleaner, has no parameters, B 1 B 2 have been absorbed in the definition of Q star. So, this equation is function only of kappa and kappa 0. So, our aim in a given situation, given all the boundary conditions and other constraints of the problem, is to find how Q star varies with kappa and kappa 0, and of course, how does temperature vary with kappa and kappa 0. There is one parameter kappa 0, an independent variable kappa, which is the location in space, and non-dimensional temperature, non-dimensional flux. So, we have brought down the problem into a very, very simple framework in terms of number of parameters. Now, today this equation can be solved on the computer, there is no difficulty. All you have to do is, the unknown quantity is here, and for a given radiative flux, let us say specify the radiative flux, you can find the temperature distribution by assuming some function here, integrating it to see whether it is equal to this value. If it is not true, then you adjust this continuously. So, in an iterative fashion, you can solve this equation fairly rapidly on the computer. So, all it requires is some approximation, maybe some polynomial approximation for phi of kappa star, integrate it, find is it equal to Q star, which is specified, then you go back. On the other hand, if in a given problem, the temperature distribution is given to you, then you know this quantity, then it is very easy to integrate this to get the flux. So, the basic problem here is either the flux is given and you calculate temperature distribution, or the temperature distribution is given and you calculate flux. you can calculate both, one has to be given, the other has to be found. So, the more difficult problem is given the heat flux, radiated heat flux, how to calculate temperature distribution. That is a integral equation where the unknown is inside the integral. So, only method available is iterative method. You guess some temperature, integrate, find the flux. If the flux does not match, go back and adjust your assumed temperature distribution. Now, our purpose here is not to discuss the numerical solution, which can be done these days quite easily. Our aim is to get an analytical solution. To get an analytical solution, you need to make some approximation, there is no choice. So, we will adopt what is known as exponential kernel approximation. So, in this approximation, you are simplifying the angular integration part of the radiation equation, and by making the angular integration simpler, you are able to solve the problem analytically. And the particular kernel approximation we are going to adopt is that E2 of x is equal to approximately equal to 3/4 e to the power of minus 3 by 2 x, and E3 of x, which is the other one which comes in the equation, is approximately equal to half Now, if you look at this approximation, let us look at what is the, actually we know E2 of 0 should be half, E2 of 0 should be 1, because let me just write the general. If you recall, En of 0 was 1 by n minus 1. So, that means E2 of 0 is 1 and E3 of 0 is half. So, in this approximation we have ensured that the kernel approximation is exact at x equals 0 for E3, but approximate for E2. E2 should have been 1, E2 is 0, but 3/4. Now, why are we making this kernel approximation? If you look at the equation for Q star, E2 is appearing inside the integral, E3 is appearing outside. So, in case of E3, it is important that you correctly get the behavior at x equals 0. In case of E2, although you may not get the behavior at x equals 0 right, as long as the integral of this quantity is roughly right, then it is okay, because this quantity appears only inside the integral. So, that is a spread approximation. There are other approximations available, you can look it up in various textbooks, but all of them give similar answers. Answers are not very different from the kind of approximation that others make. Now, before we proceed further, we must decide what problem we want to solve. We will now look at the problem of radiative equilibrium. Radiative equilibrium is a case wherein you are dealing with a gas in which radiation is the only process. We are neglecting conduction, convection and any other heat transfer process that may be occurring. We think the radiation is the dominant process, and so we will only look at radiation as the only mode of heat transfer, and then you are assuming steady state, no change with time. So, if you assume these two, that there are no other processes occurring in the gas except radiation and the gas is in steady state, then from the first law of thermodynamics, you conclude that in steady state with radiation is the only mode of heat transfer, dq or dx has to be 0. In steady state, the divergence of the flux is 0 and the only flux of relevance we are saying is radiative flux. So, that means QR has to be a constant. So, this approximation we are going to deal with this limit. So, QR is a constant in radiative equilibrium. And in our case, a non-dimensional QR is, that is Q star, the constant, and we are treating this as a known. This is a known quantity given to you a priori, and given this Q star, you are asked to calculate phi. So, given Q star is a constant, you are asked to find the temperature distribution. So, this is a standard problem in pure radiation heat transfer in steady state, one dimension, there is no other mode of heat transfer. Therefore, dq dx is 0. So, q is a constant. So, we make the kernel approximation, which is already had been mentioned. So, with that we will get the equation which says q star is equal to e to the power minus 3 by 2 kappa plus 3 by 2 0 to kappa unknown temperature distribution e to the minus 3 by 2 kappa minus kappa star d kappa star minus 3 by 2 kappa to kappa 0 minus 3 by 2 kappa star minus kappa d kappa star. In this equation, q star is a constant, remember that. Unknown function is inside the integral. Now, how do you solve this equation? Now, having made the kernel approximation, that is replacing the complex kernel by an exponential function, we exploit the fact that exponential function is repeatable, and if it is repeatable, then you can easily differentiate this equation twice, and all of you know that e to the power minus x when differentiated twice will give you the same answer. Okay. And so, that is the feature we want to exploit in this formulation, and so we will do that. Let us now go and differentiate this equation once and then twice, and remember that q star is a constant. So, dq star d kappa is 0. So, now we write down the left hand side of the equation is 0, because dq star d kappa is 0. Then the second term is we had was 3 by 2 half e to the power minus 3 by 2 kappa will become minus 3/4 e to the power minus 3 by 2 kappa, and so if we differentiate this twice, you differentiate this twice and use the Leibniz rule. So, the Leibniz rule is important, and we had discussed that earlier in the context of shear factor calculation. So, let me just say you differentiate twice, this we need to go through carefully. So, differentiate twice, so that left hand side is anyway 0, because q star is a constant, and you will get after 2 differentiation 9 by 4 e to the power minus 3 by 2 kappa plus 3 by 2 0 to kappa phi of kappa star e to the power minus 3 by 2 kappa minus kappa star d kappa star minus 3 by 2
3
just wait a minute. Now, when you differentiate twice, let me give you some more information here. It could be 27 by 8. Minus 27 by 8, because 3 by 2 into 3 by 2 twice will be 9 by 4. Kappa to kappa 0. So, this also compared with the equation we wrote down earlier, which said Q star is I will not write the detailed one, that you can see from the previous expression written already there. So, what you see is that in order to eliminate these two integrals between these two equations, you have to multiply this equation by 9 by 4. If you multiply this equation by 9 by 4 and subtract that equation, so this is, let us call it as equation 1 and this is equation 2. So, equation 1 minus 9 by 4 equation 2 will eliminate all these integrals, and you will be left with only, I might add one more term here, I am sorry, 3 d phi by d kappa. From the Leibniz rule you get this term. So, you take 9 by 4 this equation, subtract. So, these terms are all will cancel out, they will all have 27 by 8, and so you are left only with these 3 terms. So, let me write down that equation, which finally is d phi by d kappa 3 by 4th into, okay, that is what you will get. So, let me go back and clarify what we have done. So, this term will all go away, and you are left with this term and this term, and 1 3 will cancel out, and so you are left finally with this equation. So, we have converted an integral equation to a differential equation by exponential kernel approximation. So, this approximation has been very useful to convert the original integral equation to a differential equation. So, this can be integrated very easily to get phi is equal to minus 3/4 q star kappa plus a constant. So, this non-dimensional temperature profile is a linear function of kappa, but remember that does not mean that temperature is a linear function of kappa. That is because phi, if you recall, is defined as sigma t to the power of 4 minus B2 by B1 minus B2. So, phi depends as t to the power of 4. So, it is t to the power of 4 which is linear in kappa, not temperature. Now, you need to find the constants. To find this constant, there are actually two constants. This is also unknown constant, this is also a constant, two unknowns. Of which you can assume that this is provided, okay, this is really unknown, this can be assumed as specified. So, you want to get the final answer for the heat transfer. in terms of copper. So, what you do is you plug this into the integral equation and satisfy the integral equation at say kappa equals 0. When you do that, the constant will come out as, so this is the solution. Once you have found the constant, so it will the Q star will come out as 1 minus 1 by 1 plus 4/3 kappa 0, which can be simplified to Q star is equal to 1 plus 3/4 kappa 0. This we will discuss in some detail in the next lecture, because this is a very important result which relates the heat flux to the optical depth of the medium, okay. And we will discuss the meaning of this in the next lecture.